So as I'm before I jump into the main topic of today's talk, I just wanted to advertise some of the things that we do in our lab. The lab is highly focused on doing applied translational research, and so we work on three thrusts. I would say 50% of the lab works on the thrust one, the energy, trying to make low carbon fuels and chemicals. And the main focus over there is hydrogen, and we have tried a little bit on some other chemicals like bromine and formic acid, but not much traction was received, so we stuck with hydrogen. The thrust two, the food and water, I would say 40% of my group works on that thrust area, and the goal over there is to make sustainable water and fertilizer. And the third, which I tell to my colleague, it's a mistake because I shouldn't be working on health because I'm terrible with biology or anything related to health related matters, but I'm convinced that some of the skill set that we have in our lab, mainly the use of electricity to drive chemical reactions, can be used in the health sector as well. So we work on developing oxygen concentrators, mainly after the time of COVID. So those are the three major thrust areas that we focus on, and the research approach in our lab entirely is based on this field of science, which is electrochemistry. And then here is the currency note that was released in honor of Alexander Volta, who invented this particular field. Basically, what he found in 1800 was if you use different metals, and if you have some sort of alkaline water in between, you could either generate electricity, which became batteries, or you could reverse the process. You could supply electricity and do some chemical reactions or transform things in water to something else. Right? So he was credited as the father of electrochemistry, and rightfully so. And he also happens to be the professor. Right? And I think this was the first example showing the utility of a professor. Right? Because after his discovery, soon there was translational research happening in the field of commerce. Prior to that, any commerce activity was purely dictated by the industries. After this, new industries came to place: the electroplating, electroforming, the aluminum industry. The aluminum cans are made using electrochemistry. Then the use of electrochemistry for other principles. Everybody carries batteries in your pockets. So this was the first example showing the utility of a professor too. Right? And prior to that, nobody thought professors could have any use. So that's right. So the approach that we use in our lab builds on this principle. Right? So, and in very simplistic terms, you could imagine this principle as sticking two metal electrodes and carrying out certain reactions, or vice versa. Right? So that's the principle. And you will see how we have tried to use this approach in the field of environmental engineering, mainly to treat water. And I just like to show this one slide. I don't have to preach to the choir in this room, but I like this particular article, apart from many articles that have been discussed about the challenges with freshwater access. The reason I like this article is because the predictions from this article has been pretty good. If you go back and read this particular article, which was published in, it was sometime around 2000, and they made predictions about what the water consumption would look like how much the water consumption would increase, and how much would it impact the people. And if you take the reports back from 2024 or 2023, and if you look at the numbers, it matches quite well. So that's one of the reasons why I like this particular article, and then just wanted to showcase that sometimes predictions can be true as well. So everybody understands you have limited access to fresh water, and then there are multiple solutions that has been implemented over a century to increase the freshwater access. And in our group, we focus on two major topics. I'll first talk about the part one of this presentation would focus on looking at the current desalination technologies that currently exist, and is there a way that you could improve the status quo of desalination technologies using this principle that I just talked about, the electrochemical approaches. So it was more from an exploratory kind of an undertaking, mainly from a personal interest. I wanted to see if electrochemistry has any role in this process. If it's not, that's fine, but I would like to know that as well. So that's this part of the talk. And when we looked at the desalinations, again, I'm not, as an expert or well versed in the environmental portions of the field, so I had to look around and then see what currently exists. It was a good snapshot of the current desalination facilities that exist across US, and it gives the different technologies that currently exist. You have the reverse osmosis dominating the market, and then what we quickly found was the current desalination technologies do a really good job. The reverse osmosis is a beautiful technique that works very close to what its the thermodynamic limits are in terms from an energy efficiency perspective, right? So we looked at it, and then we realized there is probably no need to bring a new electrochemical process for desalination alone. But then we looked at then why is it not practiced everywhere? Why is it that exists really large scale? You have few large scale desalination plants, but why hasn't it been implemented in a much more rapid access or a rapid way? We did this program called NSF ICORE. I don't know if anybody has done that. So basically the program is when you bring in people from academic setting and let them loose for 3 months, and have them talk to 100 people, minimum 100 people, and these 100 people should be from different stakeholders, could be industry people, could be the actual consumer, and so on and so forth. So if you're developing a product and you can't mention what product you're developing, but you got to identify 100 people and talk to them about, hey, what is needed in desalination, or in the exercise that we took, that was the question. Right, wanted to really understand what is needed in the desalination technology, right? Because simply looking at the numbers from thermodynamic standpoint, it didn't seem like there is a new need for the technology. And one of the things that jumped immediately out of those 100 was more than half of them mentioned, and this was mainly industry players, and more than half of them mentioned that if we have a good concentrate management option, that would further push this technology forward. And that's where we looked at what are all the concentrate management options. So concentrate is basically you desalinate, you get fresh water, but you're left with this concentrated salt or concentrated brine. But again, and how do you dispose it? But in the coastal areas, it's fairly simple. People just dispose it into the oceans, which is again, at least right now the regulations are not that stringent, but it is becoming stringent to just release it into the oceans as well. Right. And what happens to the inland communities? and so on and so forth. So this chart gives what are all the types of concentrate disposal options that currently exist. And this was some of the take-home message that we had, which again, I'm not an expert, so I apologize if some of these take-home messages does not accurately reflect the current scenario, but this is what we have seen. Sorry, but I will stop moving there, or just be here. So the currently 5 options account for 97% of the concentrate disposal, and what we found was most options are limited. You don't. It's not easy to create these deep well injection systems or the evaporation ponds and so on and so forth. And so we thought, what if we could take that concentrate and do something useful out of it? Right? And that's this proposed solution. This was my, the first, funded project as an assistant professor. This was submitted to the Bureau of Reclamation, and the idea was to take existing system that already is there and see how we could integrate a new technology, which would be an electrochemical based, that takes in just the concentrate produced by this desalination method and turn it to something useful. Right? So the idea goes this way. So the approach was, if I could take the concentrated brine, in this case I've simplified it, let's just assume it's sodium chloride rich brine, which is not far from what you would expect from in a brackish or water's desalination technologies, or even in terms of other desalination processes. So you have the sodium chloride rich brine. I know the electrochemistry that if I could choose the right electrode, I could knock off this chloride ion in the sodium chloride and convert to chlorine. And chlorine is a value-added chemical. Right? I know that from my chemical engineering background, if I could generate pure chlorine, there is a market to buy that. All right, so if I could generate chlorine, then I have the sodium ions left over here, and if I have a negative charge or a negative electrode over here, the sodium ions would move to the negative electrode. And if I carry out a different reaction, like say from water, if I reduce water to produce hydrogen, I'm left with OH minus. So in order to balance the OH minus ions that are left over here, the sodium ion will move and react with the OH, and I could get sodium hydroxide. And if I engineer the system carefully, I should be able to get a depleted brine out of it. And more importantly, I'm taking chlorine, hydrogen, and sodium hydroxide, all 3 value-added chemicals. Right? Now, another thing that we wanted to do was, sustainability was a key part or a key interest of my research group at the time. And we looked at, instead of taking, sticking metal electrodes and using a power supply, or like a battery or a grid to carry out this chemistry, what if we just use sunlight to carry out this process? So it can be done off-grid. You don't need electricity to carry out these reactions. Would be fully renewable and should be able to do these processes, producing chlorine, hydrogen, and sodium hydroxide. And that was the first undertaking that we did. This goes into a little bit more detail of what the exact reactions are. But I will skip this step. This is something that I explained in the previous slide. But there was one challenge, right? So the challenge was for each of these reactions to happen, right? In order to produce chlorine, I need some voltage, right? To carry out that reaction. In order to produce hydrogen, I need some voltages needed to produce that reaction, right? Now, if you think in terms of battery, each battery provides certain voltages, right? You have the alkaline batteries, which are roughly 2 volts. You have the lithium-ion batteries, which are roughly 3.4 volts. Likewise, to carry out this reaction, you need roughly 2 volts, right? So, which means I need to find some sort of arrangement which could get stacked up and provide the necessary voltage. And semiconductors, which are typically used for these purposes, you have a range of semiconductors. Semiconductors, would go from titanium oxide, which are something that you use for your sunscreen. It's roughly around, it could provide 3 volts. And then that's the reason why it's used in sunscreen, because it will absorb sunlight and get excited carriers, and it would prevent it from reaching your skin. Right? So that's the reason titanium oxide or zinc oxide is used in sunscreen. But I can't use that process over here if I have to maximize the sunlight, because I wanted to use enough spectrum of sunlight, not just the UV spectrum, right? So if I have to use enough spectrum of sunlight, then the type of semiconductors that I have to use should be producing a voltages roughly 1.5 volts, which means I need 2 semiconductors to carry out this process, right? Because I need minimum 2 volts, so I need roughly 2 semiconductors to do this process. So that was one of the challenges. So how do I have 2 semiconductors identified? And one semiconductor should do the process of hydrogen production, the other should be doing the chlorine production. And these semiconductors should be stable, because these are going to be immersed in water in a concentrated brine solution. So it needs to be stable. And the overall motivation of this technology is to hopefully lower the cost, right? Because the cost is one of the key challenge to come up with concentrate management options. So it has to be lower the cost. So the material that I should be making should be dirt cheap, and if it has to be dirt cheap, then it has to be made with dirt, and preferably local dirt, so that we don't get tariffed. Right? So that's a challenge with this. So we came up with 2 approaches. So for the hydrogen producing process, we developed a material called tin sulfide. We like this material mainly because the sulfur, when it's attached to tin, makes it extremely stable for the water chemistries that we are trying to do. Right? So tin sulfide is a good semiconductor. Semiconductor is something that takes in sunlight, produces energy, and you could use that energy to carry out the reaction. And so the first goal was to make tin sulfide based systems. We have abundant tin, we have abundant sulfur, so this makes sense. And what you see in this snapshot, without going into too much detail, is it works. We are able to use tin sulfide as a semiconductor to produce hydrogen from these systems. Of course, we tried both in simulated chemistries and in water chemistry. That's again, it's simulated, but that closely relates to the actual water chemistries that you would get from such brackish water desalination facilities. As you could see that the system remained stable for up to sodium chloride up to 10 weight percentage. When it went to 20 weight percentage, we did see a decline in its performance. So that's what the efficiency curve on the y-axis shows. If you have 100%, it's a perfect material. Anything below that, you have some losses. If it's not horizontal, if it shows a downward trend, that means it's not stable. So ideally, you want a material that's 100% and remains stable. Right? And that's the ideal curve. We were able to get, for up to 10 weight percentage, similar performance, of 90-95%, which is pretty good for a system of this nature. But 20 weight percentage, we did see a decline in its performance. Now that was on the hydrogen side. We need to do the same on the chlorine side. And for chlorine, again, we chose a material system, that's abundant, low cost, and we came up with bismuth vanadate. Although, I have to admit that vanadium is not an abundant material, so that's the closest that we could get. So bismuth vanadate again was a semiconductor material. Again, without going into too much of the nitty-gritty details, what you see here is we were able to take bismuth vanadate, and if we coat it with some layer like a tungsten oxide, this system worked pretty well stable for chlorine production. And again, we did the same exercise. We took the bismuth vanadate and tried to do it in simulated water chemistries and also a simulated solution that closely resembles the brines that you would get from brackish water desalination facilities. And what you see here is, as sodium chloride concentration went up, the efficiency of the system went up. And which makes sense because there are two oxidation chemistries that happen in water. Water can by itself gets oxidized, producing oxygen, or the chloride present in the water can get oxidized, producing chlorine. Right, so the more sodium chloride you provide, the more better the efficiency system becomes. This system was fairly stable. And this snapshot doesn't give the entire timeline. We have done close to 1,000 hours for this particular, just for the bismuth vanillate system at NaCl of 28%, and we observed less than 5% degradation after 1,000 hours of continuous operation. Now, again, the motivation was to see if this technology would be useful to be integrated in existing desalination units, desalination systems, and I was very much interested in again doing translational research. So cost economics becomes a key factor. So we did some preliminary techno-economic analysis, working with some industry partners to understand where the system would go in, what would be the cost targets that they are looking for. And so on and so forth. So this gives a snapshot of a simple block flow diagram of where this system would be. The system would be over here, which we call it as PEC. PEC stands for photoelectrochemical. So this is pretty much most of the desalination facilities system ends over here, but we needed to add some brine treatment because we realized quickly that while these systems are stable in the presence of calcium, magnesium, sulfates, the system is not very stable if you have a little bit of bromide present in it, and a few other ions. So we needed to do some brine treatment, and then have the PEC, the water fed to the PEC system. So let me just quickly show you the result. Based on our current, the performance metric, we just simply did what would a cash flow diagram look like. Basically this is showing if you build a company based on this, and if it runs for 20 years, is it a profitable venture? With current performance metrics, with current cost of the materials, even though the materials were indeed cheap, but you got to build all the necessary bells and whistles around it. You have to have the right proper unit, the housing units, the support structures. In fact, the major cost was the support structure on which these reactors would be installed in large areas. And the challenge is sunlight is diffuse, which means in order for large-scale desalination facilities, you need large areas of land, which means large areas of these reactors need to be built. And the cost was pretty significant and did not show a profitable venture. It did become profitable if the efficiencies rise to 10%. What I mean by 10% is if I could use 10% of the sun's energy and convert that energy to do these chemistries from concentrate brine, then it becomes successful. But we haven't found a cheap enough system or on the same material system that we have to go beyond 4%. I think the 4% is the best metric that we got in a small lab scale. We try to do a large scale unit and the efficiencies drop. So it's a good self-realization that there exists a lot more challenges, and then clearly, we in my research group was not adequate to fix those challenges. You really need to increase efficiency and keep the material cheap. We did show that efficiencies can be improved. And we chose materials which are which are highly efficient semiconductors, and we did show that we could get 20%. So the efficiency metric can be achieved. But the problem is these materials that I show over here are only used for space applications, which means they are very expensive, not good for terrestrial, so it won't work. But just to showcase from a lab scale perspective that we could achieve high efficiencies, hopefully someone interested, and I could bring the cost down. So I will end this part. I have the second part of the talk over here, but as I transition, if you have any questions, please feel free to stop me at any point. So this project is on how to take nitrates from impaired waters and make value-added resource from them. Right? So this project is, I will show you, the economics was much more reasonable, and as a result, we did form a company, that's the Paniclean. June mentioned over here, Dr. June Lee, she is the founder of the Paniclean, and we do have worked very collaboratively with universities, but also from other industry partners like the Ideal Energy. I think they are the largest solar installers for the Midwest, who are helping us build containerized units powered by solar cells that can take in impaired waters rich in nitrates and produce something valuable. The problem about the nitrate is something that I've never focused until I came to Iowa, where we were told that you needed to have by my environmental engineering colleagues, that you need to have some RO systems, because the place where I was, it had a well, private well, but the private well did have nitrates levels sometimes during the agricultural season, reaching close to 25 milligrams per liter or 25 ppm or higher. Right, so that's how I came to realize that nitrate is a big issue. It's the most prevalent groundwater pollutant. And you could see the numbers on the right-hand side, basically saying, 50% of surveyed U.S. groundwater contains nitrates that exceeds the minimum limit, which is the 10 ppm as N. And when we looked around, again, we did another NSF ICOR program for nitrates, same thing, reached 100 customers. So we reached 100 customers, again, to understand what is where does the market lie. We found that there is an immediate market, because you have 1,700 community water systems violating the nitrate amount, and as a result they do pay fines, right? Or at least that's what we are told. And it's also been shown that you have a healthcare impact, because the nitrates does lead to the blue baby syndrome and the thyroid function disruption and so on and so forth. So you have a $1.5 billion healthcare impact that's being projected because of the nitrate processes. And so we looked at what techniques exist. Again, reverse osmosis and ion exchange do a really good job. They can, remove nitrates from your water. I have an RO unit in my home. The water treatment system. The Des Moines Water Works has 6 ion exchange units to treat nitrates before it releases water back to the river. And so RO and ion exchange exist, does a fantastic job. But again, the problem here again is concentrate management. Just like the brackish water desalination or the seawater desalination, the problem here is, what do I do with the nitrates, the concentrated nitrates that we have? So we got some numbers from the ion exchange plants that exist around US, and we were told roughly 70% of the financial burden is from the ion exchange resin regeneration process, and the brine disposal cost is roughly, it varies, but on an average it's 36 cents per 1,000 gallons inlet. So again, here the solution, the only trick that we know is to use electrochemistry. So the idea is to see if I could use, again, electrochemistry to transform these pollutants. Right, and one of the things was to see if I could take nitrates and nitrites and use the electrical field and the rest of the ions in the water and produce something valuable. We looked at ammonia as the process because it it kind of made economic sense, especially when we consulted with some of the ion exchange plants like the one in the Des Moines Water Works, because one of the methodology could be we could buy that. They could pay us to take the concentrate from them, and for us to make money, we need to make something more valuable, not just treat it. So that's where the ammonia comes in the picture. Right? And it's a significant amount. If you look globally, 30% of global ammonia demand can be supplied using nitrates in the water sources. So the solution works this way. And the challenge with an electrochemical system is you've got to have concentrated pollutants. Right? If the pollutants is not in concentrated amount, most of the electricity would be wasted as heat or doing secondary reactions. That's the challenge. Right? So if you have large amounts of pollutants, electrochemistry becomes a very attractive field to treat them. But of course, nitrates, 20 milligram, 30 milligram is still very, very small when it comes to electrochemistry. You need some things in terms of 100 milligram per liter of pollutant. So the first step is we have to either work in unison with an ion exchange plant or an RO plant that treats nitrates, take the concentrated nitrate from them, use it in an electrochemical system. In this case, it's an electrolyzer. And I don't know if you have been following hydrogen industry or the hydrogen boom that happened during the COVID. It was the expansion of these electrolyzer industries. These industries were planning to produce hydrogen, which can then be used in your fuel cell car. So the technology is very similar to that, but in this case, you'll be producing ammonia from hydrogen and not hydrogen, and you'll be using nitrates as the feedstock. So if you have nitrates as the feedstock, if it enters this electrochemical system, on the reduction side, nitrates will be converted to ammonia, and on the positive side, water will be converted to oxygen, and you prevent the ammonia moving from left side to the right side by having semi-permeable membranes or ion-selective membranes. In this case, we use something called a bipolar membrane, which allows ammonium ion to pass from the left side, but it doesn't let it go to the right side. So you get a concentrated ammonia stream in the middle. Okay. So, and then we take it for ammonia storage and so on and so forth. I don't have to tell the social impact clearly. If it makes more economic sense, it helps in decentralizing water systems and ammonia production, which has been a big push. While ammonia is cheap in US, we roughly pay $400 per ton of ammonia production. For ammonia production, it's in the other parts of the world, it's a highly volatile commodity because ammonia is produced from natural gas, and the natural gas reserves dictate the ammonia production. So, for example, in many parts of the Africa, the cost of ammonia production is over $1,000 per ton for ammonia production, and in US it's roughly $400. In Japan, it's very expensive just because they don't have the natural gas. Likewise, in Europe, especially in Germany right now, it's very expensive because the natural gas resource has been cut from Russia and so on and so forth. So people are trying to identify decentralized systems to produce ammonia, maybe in a small form or in a large form, using the feedstocks that are currently available out there. So that's the social impact that we envision. Again, here I would just quickly go through what the main finding is. So one of the findings that you do have to have is you have to remove that ammonia first, or concentrate ammonia. And for that, we developed some sort of like a 3D electrode system. What I mean by the three-dimensional electrode systems that could capture nitrates, right? So that it gets concentrated in its system. So it's almost like the carbon filter process. So it captures all the nitrates. And then if you have catalyst loaded on these electrodes, I could then apply electricity and convert that nitrate to ammonia. So that's the principle. We call it like a bait and switch approach. Basically, the bait is you apply a positive potential, so the nitrate, which is negatively charged, will come towards the positive electrode. And if you provide enough surface area, they remain there. And then you switch it, which means you switch the polarity from positive to negative, and the negative polarity enables conversion of nitrate to ammonia. So it's like a bait and switch. So this slide gives the take-home messages. We were able to identify some 3D electrodes that enabled good nitrate capture process. This particular slide talks about once the nitrate is captured, the carbon does not transform nitrates to ammonia. Like, it just captures it. You need something else to transform the nitrates to ammonia. We identified copper with a little bit of titanium in it, was able to selectively convert nitrates to ammonia. Again, we could play with the metal over here and could convert nitrates to nitrogen gas as well, because that was another project that we worked where the stakeholders were more interested in just destroying nitrate, and they wanted just nitrogen out of it. They didn't want to deal with ammonia because that requires a specific infrastructure. Not every stakeholder wanted ammonia, they just wanted to destroy nitrates. So you could play with these materials, and we do have a material combination that can convert nitrates to nitrogen. But what I'm showing over here is takes nitrates and convert it to ammonia. And then what you see here is, like, we are able to start with something like 45 milligram per liter. That's the amount that we were able to concentrate from, I believe the feedstock was roughly 10 milligram per liter or 15, I don't recall. We were able to concentrate to 45 milligram per liter, and we were able to convert it into ammonia. So we were able to achieve roughly 90%. Achieve roughly 90% nitrate conversion with selectivity of greater than 70%. The rest were mainly nitrogen gas. This particular slide just shows the reproducibility, can we do this over and over and again? So basically, that's this particular slide. For all systems, we were able to achieve over 80% nitrate removal and conversion. And the unit is shown over here. This is your concentration unit, and this the conversion unit. These are all the control systems for the necessary sensors to monitor what's happening real time. So this was all done in simulated waters. But then we reached out to the city of Hastings in Nebraska to obtain the RO reject that they have from the nitrate treatment facility. All right, I'm assuming I'm showing the city of Hastings in the right location. So they have the city faces a lot of nitrate pollution. They have multiple technologies to treat nitrate, and one of them is use of RO systems. So we went to them, we took their RO reject and tried to see what happens if I take the RO reject and feed into this particular unit. And that's the results shown over here. The RO reject had much higher concentration. It was roughly close to 100 milligram per liter was the RO reject concentration. And we did not do any pre-treatment. It was the reject directly obtained from the RO system, RO nitrate treatment system, directly fed to the unit. And we were able to achieve nitrate removal and conversion of up to 80%. The selectivity was slightly down 40%, mainly because the presence of other ions does interfere with the selectivity. So we were able to achieve selectivity of greater than 40%, but we were able to destroy nitrates greater than 80%. Now, based on that, then we developed this prototype as part of a deliverable for a USDA project. So the deliverable was, it needs to be all-in-one unit powered entirely by renewable electricity that can be off-grid. So this is the first prototype, which is a 300 gallons per day system. It involves all the necessary bells and whistles, that you could directly feed it to an RO reject. RO reject system or a water treatment, or water that has higher nitrate levels. And the unit is built in such a way that it's like a one-touch system. So you turn it on, it measures the nitrate concentration, it adjusts the necessary voltages, adjusts the necessary power that needs to be delivered from the sunlight, does the nitrate concentration removal, produces ammonia and stores the ammonia, and then stores the clean water from it. So that was this particular unit, which is a 300 gallons per day. That gave us a little bit more confidence, because now we have all the necessary bill of materials to do the costing. So we went ahead and done the costing, and then we realized quickly that the nitrate concentration plays extremely crucial role in determining the cost. So as you could see, so once we exceed close to 250, 500 milligram per liter, then we become competitive to green ammonia processes in US. And if you have to reach the Haber-Bosch process, which is the traditional process to have ammonia, you really need to have really, really high nitrate concentration, right? So that was good, because then we could go and work with the customers who have such high concentrations, because this tells us I can't use this technology in an agricultural runoff, because I can't use the agricultural runoff as very dilute. This can't be used there, but can be integrated to something else which concentrates and provides that. And we did identify, for example, on the higher end of the spectrum, the wet scrubbers that are currently used for ammonia combustion produces nitrates roughly 4,000 to 5,000, 3,000 to 5,000 milligram per liter. There is a project that is currently in talk with Veolia. Who have such high concentration of nitrates, and they wanted to treat it. So we are in talks with them and with Baker Hughes, who also have ammonia combustion and hydrogen combustion engines that uses wet scrubber and produces nitrates. And the Des Moines Water Works and the Hastings come in the first bullet points, or a couple of bullet points over there. So the ongoing work, obviously we wanted to expand the scale. So we are currently doing a pilot testing in Iowa wastewater, the tech park, which is integrated with the water resource recovery facility. And the nice thing is, we could tap nitrates from two places from this facility. One, right after the effluent from the bar reactor. There the nitrate concentration is really high, which is greater than 500 milligram per liter, but it also has all the crap that comes along with it. So it will be a good test bed for us to see how the technology would work with such waters. They also have effluent that comes out of the treatment plant, and it varies sometime between 10 to 20. And when it's 20, the process is to blend and bring the concentration to 10. But we are trying to see if we could take that water stream and use that. We also are planning to work, it's a containerized unit. The idea is to move the container to the city of Hastings and use it along with the RO reject. And here the concentration is greater than 70 milligrams per liter. And then this is the progression of the systems that we made. It's a 25 centimeters squared up to 100 centimeters squared. The nice thing about electrochemistry, just as you would appreciate in your phones, is the footprint is small, right? The electrochemical systems can be made smaller and compact, and that's the advantage of it. So where real estate is a problem, electrochemical technologies could be highly useful. In terms of power, what you see on the right is a 4 kilowatt system, and basically can treat 1,000 gallons per day of water with nitrate concentrations of 100 milligram per liter. So if you have 100 milligram per liter of nitrate, you could do 1,000 gallons per day. If the concentration is lower, you could treat more, because the power is dictated by the nitrate concentration, right? And then if the nitrate concentration is high, then the gallons that you could treat goes down. This is a containerized unit that's ongoing. We are still waiting for our solar. This is a rendered image. It doesn't look that clean inside, but it's a rendered image, and we're still waiting on everything is installed except for the solar panels, the inverters, and all the necessary things to run this process. And this containerized unit will can be directly fitted to the water that's coming out of the treatment plant or to the RO reject. We have some pre-treatments there if needed, or it can bypass the pre-treatment, directly go to the concentration conversion unit, and we have an ammonia storage, ammonium, I should say, it's a liquid ammonium, not ammonium. And here is the roadmap where we are. We just finished the 2020, so right now we are at 1,000 gallons per day. We have an ongoing project, not sure if it will go to the next phase. The funds are currently frozen. But that project is to scale from 1,000 gallons to 10,000 gallons per day system. So basically, so just going up higher. But currently, we are in line to test our 1,000 gallons per day system, funded mainly through USDA and the US Bureau of Reclamation. Right. So with that, obviously, none of this is what I did. I just speak. So those are the folks, and one of the things that I'm really proud of is all my PhD students and postdocs, we come from diverse background, because I strongly believe that you need to have different expertise and experience to solve these problems. And then none of them over there are also electrochemical engineers. And then I do a test when I have a student join. I give them a battery, those flat batteries, where you can't tell positive and negative unless you look at it. It's not the one with the tab. And I ask them to tell which one is positive and which one is negative when I remove the cover. Most often they fail, and I take them in, because I think they come with an outside, completely different out-of-the-box perspective, and that has been very helpful in solving the problems that we do. Because if it's, I am too much in electrochemistry and I miss the big picture or the other solutions that are available. All right, so that's my end spiel. Global warming is a challenge. You need clean water and energy, and it has to be cheap. That's one of the reasons why all the projects that we do, we start with doing some economics. If it's not cheap, the likelihood of we carrying out this is very low. Yeah, that's pretty much it. All right, thank you.
Thank you for the wonderful lecture. I was wondering, for the 2025 year plan, the roadmap, what are your plans for this prototype?
So here the prototype is so the plan was to have this 4 kilowatt unit to go to 5 kilowatt, but to have multiple of 5 kilowatt units. So we need roughly 50 kilowatts to carry out 10,000 gallons per day. Roughly, if it scales linearly, which we expect it to, but 50 kilowatt. But the challenge is we make these electrolyzers using off-the-shelf components, and the OEM, the manufacturers that are out there, it's hard to buy systems that can enable you to build more than 5 kilowatt. So you have 5 kilowatt, it's just like stacking many batteries, just like the Tesla car. So you have 1,000 small batteries that gives the necessary power rather than one large battery. So that's the same principle. So you just stack 5 kilowatts, multiple.
Thank you.
Right. Any other questions?
So you said the RO reject from a Des Moines or a Hastings similar concentration, about 2,000?
So the ion exchange reject that the ion exchange, the constant brine that we get from Des Moines Water Works varies.
Okay.
So the highest we got from them was close to 500 milligram per liter. The lowest that we got from them was roughly 100 milligram per liter. So it varies. We have done with Des Moines Water Works as well, but I've not shown that result here. But yeah, that's because of the seasonal variation, they have that.
And the Hastings, how much?
Roughly 70 milligram. I mean, it's always greater than 70. We have not seen anything what we got from them greater than 100 milligram per liter. And again, I think that's because they in their system they have some blending happening.
Yeah.
So they make it to, so that's the thing. It's not directly from the RO reject, but after blending whatever it is.
So how much it can reduce the nitrate content? So if it is 100 milligrams per liter, then if we pass how to convert it?
Yeah, we have shown up to easily below 5 milligram per liter. But we stop at 10 milligram per liter, mainly because below 10 milligram per liter, you pay more energy tax to convert from 10 to 5 and so on and so forth. So it's, from an operational logistics standpoint, it makes it more easier to make it to 10 milligram per liter, and if you wanted to reduce it, you just mix it with the fresh water.
That's what Hastings is doing, they go close to 10 and blend water from low concentrations.
Because, as I said, the problem with the electrochemistry is like once you go below a certain concentration, even though you put a lot of electricity, much of the electricity would get wasted to do something else. And that is roughly 10 milligrams for us. If you go below that, it becomes a challenge.
Or is there any analysis like coming down to something more reasonable concentration, let's say 50 or something, and then you go through a simpler arrow system or something?
Yeah, great question. So this is something that we have been working with the Hastings people to understand what might be a better spot to stop kind of thing, because one of the things that I've not shown over here is the energy efficiency of these systems. The energy efficiency is directly proportional to the electricity that is being used for this process. The energy efficiency is high at higher concentrations, and you could see that it slowly goes down as the concentration goes down. So at 50 you would still be at pretty decent concentration, and that would enable these systems to be better integrated. And that's something is part of the pilot project, as well as one of the things is to find out what would be the better operating range for this technology. You don't have to go all the way to 10. Maybe take it to somewhere level and then step in. Yes.
In one of the slides, you showcased the conversion of nitrate to ammonia using copper and titanium. Can you explain what the role of copper and titanium is?
Yeah, so first of all, we don't use any more copper and titanium. I've just not mentioned the material because of the proprietary reasons. But the copper titanium also works. So the role of the copper is simply acts as a catalyst. So when you have nitrate to ammonia conversion, you have some barrier for that reaction to happen. And this barrier is decreased by using a certain catalyst, and that was copper and titanium combined. And when we use simply just copper, there is conversion, but not as efficient as when the copper is mixed with titanium. And so that's I don't know if I answered your question, but the role is mainly to act as a catalyst to lower this barrier for this reaction to happen. But we went away with copper, titanium, mainly because for extended hours of operation, we did see small amount of copper leaching into the water. So that was like taking one pollutant and putting in another pollutant in. So we moved away from copper now. So there is no copper in it. But for this, these results are all like with copper and titanium.
Thank you.
Right, again, thank you so much.